Hi everyone. In today's video, we are going to be looking at Unit 3 of IGCSE Computer Science. This is the 2023 specification, the most up-to-date. So this one will be good for students who are sitting their exams in spring 2023 or later. I think this should be good until at least 2025, possibly beyond, depending on the changes they make. So Unit 3 is a monster. It's like the biggest, probably the biggest unit, certainly the biggest theory unit in the course. This is going to be split up into 3 videos. This is part 1. Okay, so before we get going, I want to share with you how I suggest you use this video. So this video series is designed for students who have already learned this content in class already, but maybe feel a little bit confused about how everything fits together, or want to check their understanding before a test or exam. This could also be used as a kind of crash course for students who have progressed to A level or IB diploma or some other syllabus, but maybe lack some prerequisite knowledge. Maybe they missed out on IGCSE and you want to go back and get some kind of baseline before progressing. Could also be used for teachers who want to prepare for delivering this unit for the first time. It's a good place to get all the main points in one area. Just a little word of warning though, if you are using this video to learn from scratch, that's okay, but please don't just attempt to watch this whole video or the whole series in one go and trying to learn everything. Otherwise, you will get frustrated because it is a lot of information. Just for some context, this unit, so the whole series, would take me about 2 months to teach in the classroom. Okay, so if you're trying to learn this in an afternoon, probably not going to have a good time. Okay, so if you are doing that, I split the video up into kind of clear sections. Let's go for 1 section per day, and you should be complementing this overview video series with some other resources and some other exercises. Please ask your teacher for recommendations, or if you're not sure, you can leave me a comment and I'll try to recommend some things that I use in my classes. Okay, this sort of slower pace of study will help you learn much better and be a lot less frustrating. Okay, so let's dive into the video. So let me tell you what I am expecting you to already know so that you can get the most from this series. So the first thing that I'm expecting you to know is a little bit of Unit 1, data representation of this course. So obviously there's different ways of structuring the syllabus, different teachers do different things, but this should definitely not be the first unit that you study. So yes, I am assuming you know all about binary, all about hexadecimal, and that kind of thing. Ideally, you will have a little bit of programming experience. Now, this is not absolutely mandatory. You can still follow this if you've never programmed before, but it would be really helpful if you have an understanding of what a computer program is, and know that they are the things that make our computers work. Okay, so that's pretty useful. And of course, you should be pretty comfortable with English. There will be some new words in here, so please pay attention to them, note them down, learn their meanings, put them into Quizlet or something like that when they do come up. I also really encourage you to turn on the subtitles if you're watching on YouTube, but please be aware they are going to be automatically generated, so there will be some errors. All right, let's take a look at what we're going to learn. So Unit 3 is kind of split into 4 parts. So the first part is 3.1 computer architecture. So here we're going to be talking about the CPU, the processor, and all of its various components. Really important process called the Fetch-Decode-Execute Cycle. Ways we can improve CPU performance, and also something called embedded systems. And that will be the entire first video that you are currently watching. The second video is going to be about input and output devices. You're basically going to have to learn how a bunch of different devices, including sensors, work. Here's a complete list on the screen. The third video is going to be data storage, that's section 3.3. So we're going to cover primary memory, secondary memory, and a couple other things like virtual memory and also cloud storage, cloud computing. That's going to be a combined video with the final part, which is network hardware. There's not a huge amount of this in the syllabus. So we're going to learn about network interface cards and routers, so a little bit of basic network hardware, and the concept of MAC addresses and IP addresses. So that's basically an opportunity to practice your hexadecimal. Okay, so this is what we're going to learn. 3 videos. This is going to cover 3.1, Video 2 is going to cover 3.2, and video 3 is going to cover both 3.3 and 3.4. Okay, let's start. So we're going to take a look at basic computer architecture first of all. So we have to go back into history a little bit and learn about this man. So this is John von Neumann, occasionally pronounced John von Neumann, and he was a Hungarian-American mathematician and computer scientist. In 1945, he did something really, really important, and he basically standardized the basic architecture of a computer. And what he did is basically still used today with very little modification. He was not alone. He built this on the back of efforts from many other people throughout history, such as Babbage, Lovelace, Turing, and many, many more. Okay, so what exactly does his architecture look like? Okay, so his architecture, which is the layout of a computer, the components that we have and how they interact, is often called the three-box model. This is a diagram. Okay, so we have a processor, and the processor is responsible for executing program instructions. Okay, so this word executing just means doing, performing, carrying out. Where do these program instructions come from? They are stored in a computer's memory alongside data used by those programs. This idea is called the stored program concept. And then the final box is the input-output controllers. So these enable us to connect devices like keyboards and displays to enable human-machine interaction. And these three things are all connected basically by wires, and that's called the bus or the system bus. Okay, and that's how data travels between these three components. So this is the basic model. Okay, you got processor, you got main memory, you got input-output, and these things talk to each other through the system bus. Let's take a slightly closer look at each of these elements. Start off with the processor. This is a processor over here, this is a CPU. So as we just talked about, it's responsible for executing program instructions. So a really key idea is that the processor and main memory are constantly working together to exchange instructions and data. And this is called the Fetch-Decode-Execute Cycle, more commonly just called the Fetch-Execute Cycle. So you may hear me say that, don't get confused, they are the same thing. So the word fetch, or the fetch stage of this process, just means that the processor goes to main memory and asks for the next instruction. It sends a signal requesting the next instruction. And then it's returned from main memory to the processor. Then decode means that the processor looks at the instruction it just received and tries to understand what it means and figure out how to actually execute it. There's a lot of different instructions. Could be an addition, could be a multiplication, could be loading something, saving something. So it's going to figure out what it needs to do to actually carry out that instruction. The next step is execute, which, as we talked about previously, means that the processor is going to carry out or do the instruction by kind of using all of its various other components. Okay, and this process is constantly happening on a computer. This fetch, decode, execute, billions of times per second in most cases. Okay, so it's really, really fast, and it is basically the whole life cycle of a machine. It's constantly happening. So that's the processor overview. Now let's look at main memory. So the job of main memory is to store program instructions and also data that is required by those programs. Now, you'll hear me say like instructions and data, or instructions or data. To be honest, the processor and main memory, they don't differentiate between instructions and data. Everything's just an instruction. Even a piece of data is just an instruction. Okay, so the difference between these two terms is not super important in von Neumann architecture because they're stored together and they're kind of treated as the same thing by the processor. So in modern computers, a technology called RAM, random access memory, is used to implement main memory. We will learn more details about RAM in video number 3. So you can think of main memory as basically a table, okay? A table with two columns, address and data/instruction, or just instruction. So the memory address is basically a unique number that identifies one specific cell of the table, or one specific memory location. So for example, it's kind of like a variable in programming. Actually, variables in programming will are kind of a human interface for one or more memory locations in the computer. So if this is the address of one particular memory location, this is the data that lives inside it, the instruction that lives inside it. We can easily change the instruction that stays in a memory location. And this is done all the time when your computer changes program. Okay. So if we want to find a particular instruction, all we've got to do is we know its address and we send that address to RAM, and RAM will return that instruction back to the CPU. Let's talk a little bit more about what exactly a computer program is when we're talking about hardware. So you hopefully have a little bit of experience writing programs with a high-level programming language like Python or Java. Now, something you may not be aware of, that we will learn more about in the software unit, is that all of the programs you write must be translated into binary so that a computer can understand them. There's a few ways of doing this, but they're not relevant to this unit. So the full program that you write, even if it's a very short program in terms of like lines of Python code, that's going to be translated and then broken down into loads and loads of tiny steps that do very, very little, called instructions. Okay, so when we're talking about an instruction, that's what we mean. It's like it's not a line of Python code, because one line of Python code could become many instructions. But you can kind of think of it as like one line of the program, one statement, one operation. Okay, so each instruction has an opcode, which can be add, subtract, multiply, divide, load, save, bunch of other things. And it has an operand, which is the data that the instruction uses. A list of opcodes is stored in the processor, and that's called an instruction set. Every different type of processor might have a different instruction set. So that's a challenge when translating high-level language into binary, because it depends what kind of processor you're going to run your code on. Okay, let's learn a little bit about input and output devices. This will mostly be covered in video 2, but let's just get an idea of what they are before we move forward. So input devices is anything that allows a user to kind of send information to the computer so that it can be controlled. Whereas output devices are kind of the reverse. They allow a computer to kind of show its information, display information in a way that is understood by a human in some form. Okay, so computers basically follow this input, process, output workflow where a user inputs some data, the computer does some processing, some kind of calculation or manipulation of that data, and then output is that the human gets whatever result they were looking for. Okay, to give you an example, if I'm writing something on my computer, the input would be me pressing a key on my keyboard. The process would be the computer understanding what that key press means, putting it, going through the keyboard application, going through the right app, and then outputting something on my display that hopefully lines up with the character that I pressed. So input and output devices can both be considered as peripherals, and these are devices that are kind of external to the main computer. Okay, now things like laptops and phones have input and output devices built in, right? The screen and the keyboard is part of a laptop, but they're still considered peripherals because they're not part of like the von Neumann architecture, right? They're not processor, they're not memory, they're not controllers, they're not the bus. So they're still sort of considered external, even if they are physically attached to the machine. Here are some input devices, and here are some output devices. Okay, like I said, we'll cover these more in the next video. All right, so now we have the idea of a little bit about the architecture. Let's talk about what kind of computer we're talking about. So there's kind of two different types of computer that we're going to look at. The first is what's called a general purpose computer, and that's something like what you see on the screen in front of you. This is basically what most people consider when they think of the word computer, right? It's something like a laptop or a desktop that lets us do a whole range of different tasks. And that is the definition, something that can be used for a wide variety of tasks. I can use these computers on the screen to watch videos, play games, make phone calls, browse the web, send email, a whole bunch of different things without any problems. That's a general purpose computer. The other type that we're going to look at is called an embedded system. So you might be a little bit confused if this is your first time hearing about this, but the four things on the screen that you see right now, air conditioner controller, elevator control panel, a drone, and a microwave, all have computers inside them. But they are not general purpose computers. They are just tiny little computers, and they exist inside a larger device. And it's always something that you would not normally consider to be a full computer, right? Like you would never classify in daily life an elevator panel as a computer. They may not necessarily follow von Neumann architecture. Many of them, in fact, most of them may use a different one called Harvard. You don't need to know about that. Embedded systems basically all have the same components as general purpose, but they're much smaller and much less powerful. And by definition, an embedded system basically only does the one or two very specific things that they are programmed to do. For example, elevator control panel, you press a button, it lights up, elevator takes you to that floor. You can't use this to write an essay or to watch a video or to play Fortnite with your friends, right? You can only do a really small range of things that it's programmed for. Okay, last thing we're going to look at before moving on to the next section is a little bit more about processors now that we've covered general purpose and embedded. So in a general purpose computer, the main processor is called the CPU, and that is the central processing unit. Most of the time when we're talking about computers, we can use these two terms interchangeably. Technically, there's a little difference. And that's what a CPU looks like. Okay. In terms of size, a CPU would be roughly maybe 2.5 centimeters on each edge, something like that. In an embedded system, the main processor is called a microprocessor. So the word micro means small or tiny, so it's a really small processor. It's a much smaller and less powerful processor. Actually, this is not entirely true all the time. It's definitely much smaller. Microprocessors can be very powerful, but if we're thinking about something like a embedded system in an elevator panel, we're not going to have a lot of power there. And that's what a microprocessor looks like. So a microprocessor and the CPU actually, both of these are integrated circuits. What that means is you cannot really take these apart. They're kind of single chips that they've been manufactured as like one item. Okay, they're not made up of discrete components. Okay, so that's the end of the first section, and that's basically going to serve as an overview of computer architecture. The next thing we're going to look at is the Fetch-Decode-Execute Cycle in a lot more detail. Okay, so let's learn some more CPU components. The first category is the active components. These are the things that are actually carrying out tasks within the processor. Firstly, we have the control unit. This one is kind of like the bus. It's responsible for decoding all of the instructions that the CPU receives, and it also coordinates the activity of all the other components in the system. So it basically tells, it figures out what the instruction means, and it will tell the relevant components how to carry it out and when. The only other component you need to know about is the arithmetic logic unit, the ALU, which is responsible for doing maths. Next, we have registers. Registers are really small memory locations inside the CPU, and one register can store one binary piece of data, one binary instruction. Okay, this is memory, but it's not main memory. This is part of the CPU. The CPU needs a little bit of memory just to store the instructions that it's working on at the moment. There's a bunch of different registers you need to know the purpose of, and here are their names. I'm not going to give you the definitions right now because we're going to walk through an example first so I can show you how they work, because the definitions alone, kind of hard to figure out. And the last component on this slide is going to be the system clock, and this is an electronic signal that controls the timing of the next Fetch-Decode-Execute cycle. Okay, and there's one more thing to cover, and that's buses. So we learned about the system bus already, but actually the system bus consists of 3 different buses. Firstly, we have the data bus. The job of the data bus is to carry data or instructions between the CPU and main memory. The address bus carries memory addresses between the CPU and main memory. And you'll see exactly how these work together in the upcoming example. Final bus is the control bus, and that carries control signals sent by the control unit to various parts of the system. Basically, this is used as a way for the CU to kind of activate a particular component to carry out a certain task. Okay, let's walk through a fetch-execute cycle. So to start off, the address of the next instruction is stored in the program counter. First step is that this gets copied over to the MAR. After it gets copied, the program counter will increment, meaning +1, pointing to the address of the next instruction. So we're going to have C8 in here now. Now that we're in the MAR, this value, the C7, this address, gets sent along the address bus over to main memory. Okay, when main memory receives this address, it does a table lookup, and it will try to find the row that corresponds with the address it just received. Okay, so here we have C7, so we're going to look at row C7. Then it finds the data that is stored at that address and sends back a copy of it along the data bus back to the processor, and that gets stored in the MDR, the memory data register. After it arrives in the memory data register, it gets copied again and sent over to the current instruction register. Now, once it's in the current instruction register, the control unit does a little bit of decoding. So the control unit is going to split this up into opcode and operand and figure out what kind of operation it is and how to execute it. Once it's figured it out, it'll then coordinate all of the other CPU and system components to actually execute the instruction. If this is a calculation, let's say that this instruction means add 1, for example, it's going to send a signal to the ALU, who's going to actually do add 1, and the result of that calculation gets stored in the accumulator. Okay, so if we're adding 1 to 0, that ends up with 1. Okay. Then the system clock will signal, and it's time to start again. So this time we go back to the program counter, and we see that we have C8. Okay, so C8 gets copied over to the MAR. It then gets sent back along the address bus. We find the instruction stored at C8, send that along the data bus, gets copied into MDR, copy the instruction into the CIR, decode it, and execute. Let's pretend that this means multiply by 2. Okay, now we go back. Now our program counter actually should have incremented, and we do the cycle again. Okay, copy C9 over to the MAR. This time I'll remember to increment the program counter in the right place. Copy the value from MAR along the address bus to main memory, find the piece of data in the right spot, send it along the data bus, stored in the MDR, copy to CIR, decode, execute. And let's say this one means multiply by 2 again, for example. So we'll store, the ALU will do that, and we'll store the result in the accumulator. Okay, system clock activates again, back to the program counter, CA this time, copy that over to the MAR, send CA along the address bus, find the data stored at that position, send it back along the data bus stored in the MDR, copy it over to the current instruction register, decode. Let's pretend that this one means end program or maybe just output or something. So we stop here, and that's the end of this particular program. Okay, so that's our little walkthrough of the Fetch-Decode-Execute cycle. Okay, let's review all those components we just talked about in terms of registers. So we had the program counter, which is the first register that we interacted with, and that stores the memory address of the next instruction. We had the memory address register, which stores a memory address that is sent to main memory. We have the memory data register, which stores data that is sent to or received from main memory. We didn't see an example of the CPU sending data to main memory, but it absolutely does happen. If you consider operations where we just want to load something or save something, that's when the MDR would send data to main memory. We had the current instruction register, the CIR, that stores the instruction that's currently being executed. And finally, we had the accumulator, our general purpose register, which stores the result of calculations performed by the ALU. Let's review the full Fetch-Decode-Execute cycle and see if you can remember all the steps. First step, system clock sends a signal that the cycle is about to start. Second step, the address in the program counter is copied to the memory address register. Then the program counter increments +1 to the next instruction's address. The address in the MAR is then sent to main memory via the address bus. Main memory does a lookup and then returns the instruction at that address via the data bus back to the CPU. When it hits the CPU, it gets stored in the memory data register, the MDR. Then it gets transferred to the current instruction register, the CIR. At that point, it gets decoded by the CU, and then the CU will, after it's figured out what kind of instruction it is, it will coordinate all the relevant components to execute the instruction by sending signals via the control bus. Once it's executed, it's time to start again, so the clock will tick to initiate the next cycle. That is the Fetch-Decode-Execute cycle. Really important, quite complicated, loads of terminology to remember. Take your time learning this. Okay, the final little section of this video is going to be talking about how we can make our CPU or our computer in general perform a little bit faster. So there are 3 ways that we're going to learn about that this can be done. First way is to increase the clock speed, the speed of the system clock. Because the cycle happens once per clock tick, if we make the clock tick more times, we're going to get more cycles. Okay, so more instructions will get executed per second with a higher clock speed. Now, a CPU is actually generally not a single processor. It's actually a bunch of different processors together. It's very common that it consists of multiple processors, and these are called cores. Each core has its own registers, although some of them are shared between cores. It's very complicated. But basically, you can think of it as a unit with multiple processors. Each of these cores can execute one instruction at one given time. But if we add multiple cores, that lets our computer really multitask. So, if we have one processor that can execute 1 billion instructions per second, and we add a second processor that can execute 1 billion instructions per second, we can now execute 2 billion instructions per second, in theory. It's not always that simple in reality, though. And the third and final way that we will learn about is adding something called cache memory. And this can store the most commonly executed instructions, which means that we don't need to spend excessive time accessing main memory, which is, although very, very fast, relatively much slower than cache memory. Okay, cache kind of works like this. If we're going to execute an instruction, we first go to the cache. If it's there, then yes, we can load it straight from the cache. We've saved a bunch of time. If not, we go to memory. If the instruction we want is in cache, we call that a cache hit. If it's not in cache and we have to go to memory, we call it a cache miss. So let's go a little bit deeper on those 3 techniques, and then we're going to wrap up the video. First thing is about clock speed. So the frequency of the system clock is measured in a unit called hertz. 1 hertz means once per second. For a typical laptop, like my MacBook Air, for example, a typical clock speed might be something like 2.2 gigahertz. This is 2.2 billion hertz. You do get faster ones than this, especially in desktop computers. Powerful desktop for gaming might be about 4 gigahertz. That means 4 billion clock ticks per second. That is insanely fast. It is possible to increase the speed of your CPU's clock, and this technique is called overclocking. But this can generate a little bit excess heat. Don't do it if you don't know what you're doing. Also, clock speed is not necessarily as important as you might think. It's definitely not the only factor in computer performance. There's a lot of other bottlenecks that mean, high clock speed might not be quite the huge factor you think it is. Okay, the next thing is cache. So cache kind of has different levels. Basically, the idea is the level 1 is like closest. It's inside the CPU. It's the smallest and it's the fastest. You can see this diagram here, right? Bandwidth increase. That's the speed of access. Okay, and you can see that it's basically level 1 is the fastest, smallest, and closest to the CPU. Level 2 and level 3, although not pictured, are slightly slower, a little bit larger, a little bit further away, still faster than RAM. Okay, and that's basically about cache. Okay, very last thing is cores. So here's a little kind of heat map of what exactly it might look like on a CPU. Okay, so you can see that there's 4 cores here. They've got a queue to communicate, and you can see that they have a shared level 3 cache. So level 3 cache is external to the CPU, but each of the cores will have their own kind of internal caches as well. So actually, every CPU that you will buy today is multi-core. Single-core CPUs are obsolete. You don't get them anymore. At least you would not find them in a modern general-purpose machine. In terms of how many cores you need, I think 4 cores is probably like the minimum that would be considered acceptable, although apparently dual-core, 2-core machines do kind of still exist. Yes, you want 4 cores as a minimum, but if you're doing something a little bit more computationally intensive, you probably want 8 cores, 16 cores, or maybe even 32, or possibly more. Okay, that is the end of the first video. Thanks for sticking with me. I hope you found this informative. I hope you were able to follow it okay. All of the syllabus section 3.1 has now been covered. And I've also given you a little bit of preview in terms of like input-output devices for the upcoming sections. Strongly recommend you stop here, revise your notes, find some ways to test yourself, do some practice questions before you move on. Thanks again for watching, and I'll see you in the next video.